So this is the fourth video on chapter 11. This video will focus on the quantum mechanical model of the atom. So we finished with the third video with the fact that the Bohr model of the atom was good, but only explained the hydrogen atom structure. And so it's not good enough to explain other atoms. So a new model was needed. And so we also have seen that Einstein determined that light acted as a wave-particle duality. So you can see light as a wave or a particle. And so other scientists like de Broglie and Schrödinger also determined that electrons could also have a wave-particle duality, which means electrons could be thought of as wave and particles at the same time, depending on the problem you have to solve. So that's how the quantum mechanical model of the atom was born. And it's thanks to Erwin Schrödinger, an Austrian scientist, that applied the mathematics of probability and the ideas of quantizing energy to the physics equations that describe waves, resulting in an equation that predicts the probability of finding an electron with a particular amount of energy at a particular location in the atom. So the result is a map of regions in the atom that have a particular probability of finding the electron. So what does it mean? For example, let's look at this coordinate x, y, z. At the coordinate 0, 0, 0, you have the nucleus of an atom. This atom has electrons, and let's say you're able to take pictures of the electrons as it moves around in time. Whenever you take a picture, you see the electron as a blue dot. And you take thousands of pictures that you superimpose on each other. You superimpose all those thousands of pictures, and you will obtain this density plot where you see dots. And you can see that the dots represent the location of the electron, and we can see that the electron seems to roam around the nucleus more than far from the nucleus. The density of the dot increases as you are nearer the nucleus and decreases as you are going farther from the nucleus. And so this density plot is like a probability plot of, it shows you where you have the most chance of finding the electron. So an orbital is one of the many solutions to the Schrödinger equation that represents a space where there is a very high probability of finding the electron when it has a particular amount of energy. So these electrons we see as blue dots have always the same amount of energy. And with time, you can see that it moves around. And so an orbital, to get the orbital, you set the probability of finding the electron at 90 or 95%, and you get an envelope. So the figure A here is like the same as the first figure. You know, it's a density plot, but it's smoother. And then figure B here is the orbitals that corresponds to the envelope that encompasses the region where you have 90 or 95% chances of finding the electron within that region. So here it represents a spherical orbital, and schematic B is like the envelope that comprises or contains inside 90 or 95% of the position of the electron if you were able to look at where it is. And 10 or 5% of the time, the electron will be outside that envelope. So that's what an orbital is. It's a map or that shows the region where the electron will be found 95 or 90% of the time. So in Schrodinger's wave equation, there are 4 integers called quantum numbers that quantize the energy, because the idea of quantized energy is still valid. And so the principal energy levels are symbolized by n, and n specifies the main energy level for the orbital. So if the nucleus is below the level n equal 1, so the nucleus is down there where the energy is the lowest, when you move away from the nucleus, the energy goes up. And one of the first orbital would have its energy at the level n equal 1. And then another orbital or another sets of orbitals would have their energy at n equal 2. And then etc. n equals 3, n equals 4. So these levels symbolized by n are the energy levels, the principal energy levels. They represent the shells. We also call them the shells. And each principal energy level or shell has one or more sublevels or subshells. So if you look at the table below, you have the shells symbolized by n equal 1, 2, 3, 4. And so for the first shell, there is only one subshell, right? Because the number of subshells is equal to the principal energy level, which means if you're in a level, principal energy level 1, then there will be only one subshell in that level. In the principal energy level n equal 2, there is 2 subshells, and they are specified by letters S and P. The quantum number that designates the subshells is given by a letter. And so when it's one subshell, it's S. 2 subshells, it's the S and the P. Then in the principal energy level n equals 3, there are 3 subshells, and they are called the S, the P, and the D. And then in the principal energy level 4, there are 4 subshells, and they are named the S, the P, the D, and the F subshells. So these S, P, D, and F are subshells or sublevels. And each kind of sublevel has orbitals with a particular shape. So remember how orbitals are representing are shapes that represent the probability map. And those probability map are set to a 90% probability of finding the electron in that region. So that's what orbitals are. And so orbitals are subdividing subshells. And so in this energy diagram, we see that level 1 has one subshell, and it will be called the 1s subshell, but also the 1s orbital. The s subshell contains only one s orbital. Then in level n equal 2, you have 2 subshells, the s and the p. The s subshell only contains one s orbital, but the p subshell contains 3 p orbitals. So there are 3 p orbitals in the p subshell. Then if you move up into the third level, n equals 3, there are 3 subshells, the s, the p, and the d. Again, the s subshell contains only one s orbital. The p subshell contains 3 p orbitals, and the d subshells contains 5 d orbitals. And then you see part of the level 4, and we see only the s, the p, and the d subshells. And we don't see the F, but there are 7 F orbitals in the F subshell. So these you have to remember. The 1s orbital, 3 p orbitals, 5 d orbitals, and 7 f orbitals. So what do orbitals look like? That was representing the s orbital. S orbitals are spherical and they are centered at the nucleus. So how does the 1s subshell differ from the 2s subshell? It's just increasing in size, but they are both centered around the nucleus. The nucleus is at the coordinate 0, 0, 0, and it just gets bigger in size. The sphere is larger. This is the shape for the p orbitals. The p orbitals are made of 2 lobes, or we also call those dumbbell shape. There are 3 p orbitals. We know that there are 3 p orbitals in the p subshell, and that's the shapes of the 3 p orbitals. They have the same shape, but they are oriented differently. One is following the x-axis, the other one the z-axis, and the last one the y-axis. This is picturing the d orbitals. These are more complex. It's 2 dumbbell shape perpendicular to one another and in one plane. And so they are in a different plane, depending on the d orbital. The first one is in the the YZ plane. The second one in the XZ plane. The third one in the XY plane. The fourth one also in the XY plane, but the dumbbells are following along the X and Y axis instead of being in between. And then the fifth dumbbell is oriented along the z-axis, and then it's a donut at the base or around the nucleus. So these are the d orbitals. There is 5 of them in the d subshell. And these are the shape of the f orbitals. A bit more complicated, larger in volume. And so you can see, again, it's still made of dumbbells, but oriented differently. And there is like 1, 2, 3, 4 dumbbells for the ones on the bottom, for example. We don't ask you to remember those shapes, but you must have seen them. So, what is the Pauli exclusion principle? So, it says that no orbital may have more than 2 electrons. So, in a given orbital, a 1s, a 2p, a 3d, you can only put 2 electrons at a time. And electrons in the same orbital must have opposite spins. So electrons have spins and there is only 2 possible spins. So if you represent an orbital with a square, a little square, let's say it's 1 orbital, it can be any kind, 1s, 2p, 3d. If you show it filled with electrons, you will show it with 2 arrows, one up and one down, to show the 2 electrons with the opposite spins, right? The arrow up and the arrow down are in opposite directions. You cannot put them in with parallel arrows. That's not correct. So the S subshell will then hold only 2 electrons because the S subshell has only 1 orbital. So one orbital can have only 2 electrons maximum, a spin up and a spin down. The P subshells hold 6 electrons maximum because the P subshell has 3 orbitals, and you can put 2 electrons in each, so 2 times 3, 6 electrons maximum in a p subshell. The d subshell can hold 10 electrons maximum because it contains 5 orbitals times 2 electrons each, so that's 10 electrons maximum in a d subshell. And then the f subshell can hold 14 electrons maximum because there is 7 orbitals in the f subshell, so 7 times 2 electrons each, that's 14 electrons maximum in a f subshell. So these boxes with the arrows up and down are called orbital diagrams or box diagrams. So we've seen that we can use the quantum mechanical model to describe how the electrons occupy orbitals within the atom. So we can draw orbital diagrams by drawing those little boxes and putting arrows up and down to represent the electrons. Each energy shell and subshell has a maximum number of electrons it can hold. We've seen that it's 2 electrons maximum for S, 6 for P, 10 for D, and 14 for F, based on the number of orbitals in the subshell, and the fact that there is 2 electrons maximum per orbital. And then finally, we place electrons in the energy shells and subshells in order of energy, from low energy up. And that's according to the Aufbau principle. So there is this diagram here to the right that shows you the order of filling the orbitals. And the order of filling the orbitals corresponds to the energy going from low energy at the bottom to higher energy at the top. And so you can see that first you need to fill the 1s orbital, then the 2s, and then the 2p, right? The p's are always above the 2s for the same level, right? Then in level 3, you have the 3s, the 3p, and the 3d. However, you can see here that there is an overlap between levels, between the level 3 and level 4. There is an overlap, and the 4s orbital is lower in energy than the 3d orbitals. So that means you will start filling the 4s orbital before you have finished filling the 3d orbital. But then after the 3d, it's the 4p. Then you have not finished filling the fourth level that you start the fifth level with the 5s, because the 5s orbital is lower in energy than the 4d. And you can see that the 5p and 6s are still lower in energy than the 4f. So there is a large overlap between levels as you move away from the nucleus. So orbitals that are in the same subshell have the same energy. So for example, the 2p's orbital are all at the same level. The 3p's are all at the same level. And then the 3d's or 4d's and 4f's, right? So when you have more than one orbital in a subshell, they are all at the same energy level. So when filling orbitals that have the same energy level, you can place one electron in each before you have to complete pairs of electrons. And that's Hund's rule. And you will put them parallel to each other. So all spin up until you need to complete pairs, and then you will put an arrow down. So for example, how we would do the orbital diagrams of hydrogen. So you need to know how many electrons you have to place, and we know that for the neutral atom, we need to look at the atomic number, because the atomic number is the number of protons, and if the atom is neutral, the number of electrons is the same. So hydrogen has an atomic number of 1, and so it has only 1 electron. And that 1 electron will go into 1s orbital, because that's the first orbital that comes when you move away from the nucleus. And so this will be represented as one square with one arrow up in it. And it's going to be labeled 1s. Let's look at lithium. Lithium, atomic number 3, will have, and so again, you start from the beginning. So you will fill the 1s orbital with 2 electrons, and you cannot put more, so you will have to move up into the 2s. And so the 2s orbital will get 1 electron, because there is only 3 electrons in total. So the orbital diagram will look like this. The first box will represent the 1s orbital. It's full with 2 electrons, and then you move up into the 2s to put the third electron. And the third electron will have the spin up, like represented by an arrow up. Carbon. Carbon, atomic number 6. So it will have 2 electrons in the 1s, 2 electrons in the 2s, and there is still 2 electrons, and they will go into the 2p. So 2 electrons in the 2p, because the 2p orbitals are the same in energy, you can put them in one orbital each, and you don't have to pair them. So the orbital diagram will look like this. It's 1s filled with 2 electrons, a spin up, a spin down, 2s filled with 2 electrons, spin up, spin down, and then the 2p orbitals contains only 2 electrons. Because there is 3 orbitals, they can each have a room, right? It's like children in a house. If there is enough bedrooms, each child will get its own bedroom, right? So electrons are like that too. They like to have their own room until they are forced to, pair. Oxygen, atomic number 8. So it's going to fill the 1s, the 2s with 4 electrons total. Then the 2p will have 4 electrons. And so 4 electrons in the 2p. So you will fill 1 electrons in each p orbital. So it's going to be 3 arrow up, and then you will complete a pair for one of the orbital. You have to do it this way. First, you place 1 electrons in each orbital, and you pair only if you have to. And here we have to pair 2 electrons in the 2p, because there is 4 electrons in total in that p subshell. So the orbital diagram for oxygen would look like this.